In this example, we're asked to determine whether or not this vector field, capital F, is conservative or not. And if it is conservative, we want to then find a potential function for this vector field. So the first step is to check whether or not it's conservative. And remember, for a vector field in three-dimensional space, there's actually three pieces of information that we have to check. They are the following. So if we name the component functions of this vector field, if we name these P, Q, and R, then we need to check some relationships between the partial derivatives of these things. And the first thing that we need to check is that, well, you can do this in any order, but if we just write these down in the order they were in the notes, dr dy minus dq dz should equal 0. So this is like a question mark equals 0. And then if that, by the way, if that is not 0, we stop. You don't continue on. That means that it's not conservative. But if it is 0, you then have to check the next one, which is that dp dz minus dr dx, is that 0? Okay. Again, if that answer is no, you stop, and the vector field's not conservative. If it is yes, you keep going, and there's one more to check. And this is the one, the only one you have to check in 2 dimensions, which is nice, but this is dq dx minus dp dy, and that's the final check. If all three of these are truly equal to 0, then your vector field is conservative, and you can then ask the question of what is a potential function for this vector field. Okay, so let's start by just taking all the derivatives that we need. Notice that the derivatives that show up in these things are the derivatives, so the p function here is in the x-coordinate slot of the vector field, and the two derivatives that we have to take of p are in the y and the z coordinate slots, respectively. Same thing for we notice that that's the behavior here, so let's do it. So we're going to need to know dp dy at some point, and this is going to just be cosine of y, and we're going to need to know dp dz, and that's of course 0. There's no z's in this p function. Then we go to q, dq dx, that's just going to be cosine of y. Notice that when you take that derivative, my pen is super sensitive today, so this is just cosine of y. And then dq dz is the other one that we need from q, and that's just going to be minus sine of z. Right? Next we go to the r slot. We need to know dr dx. Dr dx is going to be 0 because there are no x's in this equation. And then finally we need to know dr dy. Dr dy is just going to be minus sine of z. And at this point, let's color code these. So we need to know dr dy minus dq dz. So dr dy and dq dz are both here. They are the same, right? They're both minus sine of z, so their difference will be 0. So we can just do this by inspection now that we've written down all the derivatives. Now sometimes this requires more careful writing, just to make sure that you don't miss anything, but these derivatives are all pretty simple, so we can do it this way. The next combination that we need to look at is dp dz and dq dr. So dp dz, sorry, I said dq dr, I meant dr dx, and those are both 0 to begin with, so of course their difference will also be 0. And so step 2 is checked. Now we go on to the third step, the third and final step, at least to check if it's conservative or not. That's to check dq dx minus dp dy. And again, we notice just by inspection, those are the same, the derivatives are the same, and so their difference will be 0. And so because all three of these criteria are met, that tells us then that f is conservative. All right, now we're not totally sure yet in the notes, if you're going in order in the notes, we're not totally sure yet why conservative is so important, but it is very important. So the next step is, once we know we have a conservative vector field, then that means that there exists a potential function. So f of x little f, in this case, of x, y, z is going to be a potential function that satisfies the following property, that the gradient of little f is going to equal big F. And if our vector field is conservative, which we now know it is, then we can always find such a potential function. Okay, so let's write this down and try to find one. I am going to try to copy this, and I think I'm going to miss some stuff. I'll just take everything with the P, the Q, and the R as well. I'm going to copy this to the next page so that we have some more room. All right, and just underneath here, right, the gradient of f, whatever our f is, our little f is what the function we're trying to find, has to obey that the first coordinate function is df dx. It's a gradient, right? So the gradient is always built this way. The second component of the vector field is df dy, and the third component of the vector field is df dz. And if these are going to be equal, then we actually get three differential equations. So we get in the first component that d by dx of f, I'm going to write it a little bit weird here, but this should be equal to sine of y. And so let's just go one component function at a time. If this is true, then to get f back, what do we need to do? We need to integrate this with respect to x, right? Okay, we integrate both sides. On the left-hand side, the integral of a derivative, those cancel. This is, by the way, a partial integral, so it's ignoring all the other variables. And what we end up with here, again, sine of y is a constant with respect to x. So here we have x times sine of y plus some constant, which I'll call c1. But this constant could have function entries that involve y and z. Okay, this integral wouldn't see those if that was the case, because they don't have x's. All right, let's go to the next component. So this is d by dy of f. In this case, it should equal x cosine of y plus cosine of z. And the same idea is true here. We want to integrate out this derivative with respect to y. So we integrate both sides with respect to y. We treat everything that's not a y like a constant. So in this first integral, the x is a constant. The integral of cosine is sine. We end up with x sine of y. Plus, now cosine of z, that's completely a constant. There's no y's at all there. So that becomes plus y times cosine of z. And the same idea is true here, that this integral could miss a constant, and in this case the constant, because the integral is only with respect to y, could involve x's and z's. Okay? We have one more step to do here, one more integral. So the last case is that we have d by dz of our function f is supposed to be minus y times sine of z. And we want to integrate out this derivative, the same idea, right? So let's do it. I'll do it in magenta. So the important choices in life, what color to use for our integral. So the integral of this function with respect to z, we integrate both sides, right? And same idea here. This integral doesn't care about the minus y, that's a constant, but the integral of sine of z is minus cosine. So the two minuses cancel, and we end up with y cosine of z. But this one could miss, you're getting the hang of it, right? Could miss a function of x and y, because the integral only sees z's. Okay? And so at this point, what we have to do is kind of gather all of the like terms. So our integral has to have this term, x times sine of y. And look, in the third integral, there was no x times sine of y, but that means that must take up the place of this function c3 that was missed by the integral. So the first two integrals saw the x and the y. They got that term. The z integral didn't see the x and the y, so it missed that term. Okay, and then we go to the next one. Well, there's nothing left in the first integral, but in the second integral we have a y cosine z. That's also in the third integral. So same deal. The y and the z saw the y cosine z. The first integral missed it because there was no x in it. So therefore we have to set c1 equal to y cosine of z. And then what's left is just this term, this potentially unknown constant or unknown function with respect to x and z. We don't need it though, right? Because there's nothing missing from the x and z integrals that didn't already show up, right? And so what we can do is just say, okay, we can just cancel this out and say, all right, just make that equal to the zero function. Okay? So in reality, we can make that equal to any constant. We can't make it equal to any other function of x and z because in that case it would have shown up in these two integrals, but it didn't, right? And so we're ready to draw our conclusion now. This conclusion is then that our potential function for this vector field, we just need all the yellow, all the orange, and we've zeroed out the pink, right? So what's left here? Our potential function is x times sine of y plus y times cosine of z. That's a potential function for the vector field that we were given right here actually. We copied it over, right? So that's our potential function.